The burst of interest nowadays is primarily related to the fact that among these category of objects we observe very luminous phenomena with a typical luminosity 100 times higher than average type 2N or core-collapse supernova. This slide shows you the theory of evolution, stellar evolution from the birth of the star to their death. Stars are born with a salpeter mass distribution function. We know certainly that low-mass stars end their life as white dwarf, getting rid from hydrogen envelope and becoming for a short time by beautiful planetary nebula. Almost all of them quickly cool down and multiply the symmetry of cool white dwarf in our galaxy, and somehow less than 1% of this object in binary system grows Chandrasekhar mass and explodes as thermonuclear supernova, or observationally supernova 1A. Massive stars evolve to core-collapse, producing a huge family of type 2 or 1B, 1C supernovae. Here is misprint, the hero of my talk, type 2N should be there. Maybe it would be interesting for audience that the ratio of thermonuclear supernova to core-collapse is 1 to 7. 7 is not the density ratio in radiation-dominated shock.
The duration.
Huh?
The duration.
It's just a phenomenological ratio. I just trying to joke. Supernova type 2N a highly diverse category of objects, and you may find a lot of subtypes of this category as you want. In fact, possibly we could separate something like 4 or 5 main subtypes of this category of objects. The story begins with the Schlegel paper, who separated among type 2 supernovae small category of objects with this particular characteristics. All they had narrow emission line H alpha. Now we know that some of these guys have no hydrogen at all, and in this situation they show helium-1 lines in their spectra. Anyway, narrow lines on top of broad components. Blue continuum, slow evolution, photometric, and weak or no absorptions. Fortunately, at that time, I was just looking at similar objects. So it took not so much time to understand that these phenomena are related with possibly with the interaction of the supernova with the dense circumstellar environment. Indeed, please look at these two cartoons which show type 2N, archetypical supernova 88Z, and type 2P. They differ dramatically in the sense that in type 2P at the photospheric epoch you see P Cygni absorption P Cygni absorption components and emission components, generally P Cygni profiles, which indicate that you have photosphere inside of extended envelope and atmosphere which scatters radiation in lines, thus producing these particular line profiles. You don't see something like that in type 2Ns. The quasi-continuum is composed by superposition of emission lines, mostly iron 2, this bump. Some iron 2 produces emission in H-alpha region, calcium and oxygen. You see that apart from broad lines, you find very narrow unresolved lines. And there is also some intermediate width component, which I consider somewhat below. So I published in the same year a paper where I connected phenomenon of type 2Ns with the interaction of supernova with high-density circumstellar environment. Good estimate of the density of the wind follows from the analysis of the light curve, bolometric light curve of one of the supernova type 2N, 87F. And it produced a huge number. The wind density parameter, which is the ratio of m dot to velocity of the wind, is about 10 to 17. If you multiply it by wind velocity, you should be able to produce m dot. But at that time, I didn't know the wind velocity of this kind of supernova. Here you may compare the type 2N light curve and typical behavior of type 2P, normal supernova type 2P at the late epoch. This is radioactive tail, which corresponds to mass of radioactive nickel of 87A in large Magellanic Cloud with the ejector 8 solar mass and energy of 110 to 51 ergs. 2 orders of magnitude difference at the stage of 1 year. That's type 2N. Now we know that majority of type 2Ns have, if you look at the H-alpha with a good resolution, you find on top P Cygni line, which forms in the wind. And this line shows that the typical wind velocity about 100 kilometers per second for average type 2Ns. Of course, there are some deviation in higher direction and lower direction. With this velocity in hand, you may produce m dot, which is tremendous. 1/100th of solar mass per year. We do not observe in our galaxy something like that. Maybe Eta Carinae at some stage, at the explosion stage, might be close to this mass loss rate. But nowadays, it loses its mass with the rate 10⁻³ solar mass per year. I want to demonstrate to you interesting independent view on the mass loss rate in type 2Ns provided by X-ray data. This supernova 10JL has a light curve in I band, which is 0.9 micron, and V band 0.5 micron, very much similar to O6TF, which is type 2N, but much lower than ultraluminous GY, but anyway, it should be considered as rather bright type 2n with the magnitude exceeding minus 20. What we saw in X-ray, by the way, Chandra, it's Poonam Chandra, lead author of this paper, but observations really made by Chandra satellite. We see heavily absorbed.
All right. So if we send the Chandra data, then this is Chandra.
Poonam Chandra, but Chandra data.
They're not related. It's just by Chandra.
No. What are the data?
It's also the name of the scientist.
These data are published now, under publication now in APJ letters. We see heavily absorbed X-ray source, which indicates the column density of hydrogen, 10 to 24. It's 3 orders of magnitude greater than typical galactic absorption for X-ray source. Just a minute. Moreover, the interesting feature of the spectrum is K-alpha, line of iron, which has a fluorescence nature and related with cool hydrogen, or cool or weakly ionized iron. If you look at the K-alpha in more detail, you find that the maximum of emission of K-alpha a little bit redshifted compared to position 6.4, which should be in case if no scattering occurs. The effect is explained by recoil in multiple scattering. So the model, which is open square, reproduces the peak position of this. So the by and by, the X-ray suggests that in this supernova we have circumstellar material with large column density. The X-ray luminosity is very huge, 10 to 42 in 0.2, 10 keV band, and m dot, we know wind velocity in this case by optical spectra. Yeah?
Your key alpha line, you have a red part which is due, you say, by Compton scattering.
It's
Which may be due by Compton scattering.
Compton scattering. Tail. You mean red tail?
Yes, but so this is due to the wind.
Did I take into account wind velocity?
No, but it's Compton scattering in the wind.
Compton scattering in the wind, yes.
So from that, normally you can infer the order of magnitude of the wind speed.
I didn't.
Your Compton
Yes.
scattering,
Yes.
you can infer, you can compute
Compute, yes. That's
the
the
wind speed
column density.
and the wind speed also. Normally.
Yeah,
If you
sure,
suppose that the wind
sure. The wind velocity is taken into account, yeah. Here. There are two effects, recoil and Doppler effect in the expanding envelope. Yeah, sure.
And the wind velocity found with this is consistent with the wind velocity expected?
In fact, I just used this as a parameter, and I didn't try to recover wind velocity from the X-ray data because they're very noisy anyway. Yeah, it's model. It's just, yeah. You see, the error bar doesn't permit, do not permit. So it's tremendous mass loss rate, but it's generally consistent with the conclusion we made earlier from other event of type 2Ns, so it's more or less normal. About diversity of light curves. Among type 2Ns, there are interesting objects, already couple. First is 94W, and recently another object was found, 09KN, which show the light curve characteristic of type 2P, in fact. Something like plateau, drop of luminosity, and tail. In fact, it might be something like the same phenomena, but with more extended envelope and with lower energy, possibly. Our previous interpretation of 94W phenomenon with Sergei Bleinikov was based on the model which essentially was based on the spectra which possibly in some case deceived us, because one line showed us boxy line profile which indicated at that time velocity of 4,000 kilometers per second. But now I believe that we were wrong. Possibly we should exclude this line, but I haven't any justification for that even now, because we really in one case see boxy profile. But my impression is that taking into account this supernova, which doesn't show this boxy profile, possibly real expansion velocity of this swept up shell is 4 times lower, about 1,000. So anyway, the interesting feature of this, not only the light curve at the plateau, but the tail, which is more or less similar to cobalt 56 decay rate in 09KN, but much more steeper in 94W. Maybe this indicates that the tail is not related with the radioactive decay at all. So the interpretation of this phenomenon suggests that we have radiation trapping effect similar to type 2P supernova, where in which case plateau is explained as diffusion part of the light curve. And we have also indication, clear indication that the phenomenon is related with collision with the circumstellar envelope, which was not very much extended, but not also very much compact, about 10 to 15, which is about 150 times greater than typical envelope of type 2P supernova, pre-supernova. Another couple of light curves, it's 88Z, which I showed you, spectra of which I showed you before, archetypical type 2N. And supernova O8IY, which show an interesting light curve behavior with a maximum about 400 days after the detection. At this point, confident enough, this is upper limit. In this case, we possibly meet a case of collision with a distant envelope with hollow, some hollow inside. By the way, the spectra of this supernova is very much similar to the spectra of 88Z at the similar epoch, 500 days. Calcium and oxygen, H-alpha profile, iron 2 features, and H-beta, and so on. So this case is very interesting to look at in more detail. And I use simple model of thin shell approximation, which predicts more or less correctly dynamics and give you also data about shock wave velocity, the forward shock and reverse shock, which permit us to compute the luminosity of this event. And we find that in this case, we can reproduce the light curve and velocity at late epoch, which is about 3,000–4,000 kilometers per second, for two or maybe multitude of possibilities. So there is some kind of phenomena of degeneracy of supernova parameters. You cannot fix supernova ejector parameters analyzing this kind of phenomena, but at least in the frame of my model. But what is remarkable that you may predict the amount and density circumstellar medium. In both cases, these values are similar. We should have something like 3 solar mass in the range of 210 to 16 centimeters. We see that in this case, the envelope is much more extended than in case 94W, where we have 10 to 15. Here we have order of magnitude larger. And since we know the wind velocity, we know that this shell should be lost 70 years before the supernova explosion. The degeneracy of parameters of supernova may be understood in a very simple fashion. The interaction effect depends on the outer layers of ejector, which collides with the circumstellar environment. But this density distribution may be produced by different ways, using higher mass, slower expansion, but higher density, and lower mass but relatively high energy, and which also produce similar density in the outer layers. So this degeneracy doesn't permit us to recover confidently supernova parameters. Another case is especially interesting. The supernova, ultra-luminous supernova O3MA at Z.29 shows integrated radiated energy 410 to 51 ergs, which means that since efficiency of transforming of kinetic energy into radiation is lower than 0.5, you have an explosion energy at least order of 10 to 52 ergs, which indicates that among type 2Ns, or ultraluminous events at least, we observe phenomena with huge explosion energy, which cannot be produced by a standard co-collapse mechanism, which explains type 2P, for example. But it is more closer to hypernovae. So the analysis of diversity of supernova light curves suggests that the structure of circumstellar medium is different. The pre-supernova mass loss history is different, and pre-supernova explosion mechanism, pre-supernova model and explosion mechanism are possibly also differs from one case to another. So the type 2Ns is really beast of very different objects with one common property. They produce their light due to interaction of supernova ejector with the dense circumstellar environment. Even more uncertain and difficult issue is optical spectra, We had recently at tea break a talk about interpretation of optical spectra of type 2Ns. It's open issue. Nobody yet have reasonable models which is in position to reproduce any of these spectra. We have only a qualitative interpretation models. But anyway, spectra already give us an interesting look at the chemical composition of ejecta and circumstellar medium. We observe helium-rich type 2Ns and hydrogen-poor type 2Ns, which indicate that we observe different huge mass loss at different stages of supernova evolution. And we also observe phenomena of colliding of type 1bc with hydrogen-rich circumstellar matter. We just catch event at the right moment when supernova get rid of hydrogen envelope and Wolf-Rayet star, which is left behind inside, explodes and interacts with its own hydrogen envelope. It's an interesting phenomenon. Line-emitting region. We already showed the spectrum and talked about intermediate component. And I should say that standard model of interaction of supernova with smooth wind doesn't contain, doesn't have no place for intermediate component. Indeed, in this situation, we observe two shocks, forward shock and reverse forward shock propagating to circumstellar material and inverse shock propagating to the ejector. The ejector material flows into the reverse shock and piles up at the contact discontinuity. In most cases, I should say in every case of type 2N, the density of circumstellar medium is high enough to guarantee that the reverse shock would be radiative. And so cool dense shell forms at the contact discontinuity. And we expect strong broad lines from this cool dense shell, broad lines from supernova, unshocked supernova ejecta, which is cool and irradiated by X-rays. And we expect narrow lines from excited circumstellar material. But we do not expect in this model intermediate component. We produced with John Danziger two models which might explain the existence of intermediate width component as effect of shocked clouds, shocked dense circumstellar clouds. You know that the intercloud shock runs faster than cloud shock, and it is cloud shock that might produce intermediate component with lower width, because shock wave in clouds is lower. And another possibility is dense equatorial wind, which could also produce low velocity shocks propagating in the equatorial region. Even more difficult issue are the broad, smooth wings. In fact, it's in many cases when we hear words intermediate or narrow component on broad base, it's wrong. In many cases, you see some kind of unique profile, smooth profile without apparent components. I named it graceful broad wings. You don't see any hint on some kind of two-component structure. So what's the nature of this graceful profile? There are several possibilities to explain. I didn't met any more. Multiple Thomson scattering on thermal electrons could produce you smooth broad wings. But this mechanism operates only at early epoch. I introduced it in one case, 98S, and it works perfectly. It explains profiles at the stage of about 1-2 weeks. But it's impossible to produce high optical depth to Thomson scattering in the circumstellar material or somewhere else for much more later stage. In this case, in this case we observe profile at the stage 900 days, by the way. Another possibility is that in the model of shocked clouds, we have the advanced stage of shocking when Kelvin-Helmholtz instability produces fragmentation of clouds and acceleration of fragments by forward shock flow. And this could produce, if these tiny fragments emits line, they will produce nice broad wings. And third possibility is that there might be charge transfer between hot protons of the forward shock and cool materials of circumstellar clouds which inflows into the forward shock. But in order to explain the overall intensity of this line, we need to recycle cool hydrogen atom more than 1,000 times. So it's a kind of additional mechanism in addition to normal recombination or excitation of cool material. I produced some computation and found that this mechanism is unlikely because it produces a little bit weird profiles. So the stripping, cloud stripping, to me seems most likely possibility. And I just illustrate using a cartoon from paper of Hansen et al., which show you results of experiments in the shock tube where the aluminum balls, tiny ball is subject to shock wave, which propagates with a high velocity, about 70 kilometers per second. And you see subsequent stages of this interaction, which shows you fragmentation of this tiny ball or cloud in our terms, and acceleration of fragments. By the way, it's interesting to know that the shock tube has a size 2.3 millimeter long, inner diameter 0.8 millimeter. It consists of beryllium filled by some organic material, which is subject to action of 10 laser beams. The pulse has duration 1 nanosecond. So experiment is nice. But it's of course a big question. Does it really reproduce this situation of supernova? Of course. And a big question, of course, pre-supernova mass loss mechanism. We don't know about this very much. We may just suggest that it might be dense wind, luminous blue variables like Eta Carinae, red supergiants or yellow supergiants or hypergiants sometimes. I'm sorry. It may be also common envelope ejection when in binary system at the late stage of evolution, when the primary becomes, or for example, a system which consists of two normal stars, one primary becomes red giant, and the secondary merges into it and produces a stage of common envelope with ejection of the envelope, hydrogen envelope. But this mechanism of common envelope ejection should answer anyway why the common envelope stage happens at the right moment when supernova should explode. And we see the answer at the next cartoons. And of course, a violent outburst of luminous blue variables like Eta Carina in the 19th century. It experienced a violent outburst which produced ejection of a huge amount of envelope. Summary of what I talked about is that the supernova light of type 2Ns comes from supernova circumstellar collision with sometimes with a huge mass envelope, order of several solar mass, in extension with extension 10 to 15, several 10 to 16 centimeters. Diversity of light curves mostly related with the different mass loss history, density and structure of circumstellar environment. Yet we know also that supernova type 2N differ by their energy, explosion energy, very much. And three big questions remains. The optical spectra model, the mechanism of heavy mass loss of pre-supernova, and of course we don't know almost nothing about explosion mechanism of supernova, and some kind of excuse I should say about that supernova type 2N GRB connection. Three prerequisites already has been proposed which may lead to such an association. We suggested with John Danziger that the common envelope ejection may be the reason for the huge mass loss, which should be in order to account type 2N phenomena. Barkov and Komisarov explored in spiral of neutron star into the red supergiant and showed that the magnetar phenomenon inside the red supergiant may produce phenomenon something like type 2 supernova. And Roger Chevalier suggested smart idea that if we believe that common envelope ejection is the cause for the high dense circumstellar material, then it's natural to associate the explosion of supernova with the common envelope phase. And he just asked if neutron star experience in spiral, why it cannot produce also explosion of supernova type 2N. And the explosion may be produced either through the magnetar mechanism or through the formation of accretion disk around neutron star, formation of black hole, like Roger Chevalier suggested earlier in 96, I guess, yes. And in that case, like ordinary machine scenario for GRB could produce explosion, and in such a way to associate type 2n phenomenon and explosion of machine scenario. So in this case, if this might work, then why some GRB couldn't be associated with type 2n's? Of course, in this situation, we should say that in order relativistic jet to propagate through the star, it shouldn't be red supergiant. Otherwise, the jet will be stopped. And it should be compact star, maybe Wolf-Rayet, which just get rid recently from the red supergiant envelope. And again, this red supergiant envelope should possibly have favorable structure. So it might have equatorial disk structure and more or less low density polar direction. And in this case, why not we see GRB? Maybe not so strong, but maybe some kind of 98 BW. In fact, Germany associated already one type 2n with GRB, but this was short GRB, and unlikely it was related with long GRB mechanism. And in this case, the properties of GRB are unknown in other cases. So the existing data are inconclusive about this matter. So at this point, I finish. Thanks.